After finishing the axis symmetric problem, the next problem in the static structural case that we are going to solve is a static structural analysis of a lid of a plastic CD case, which is loaded in such a manner, you can see over here, it is loaded in such a manner that it will cause these tabs to break. And we are supposed to calculate the stresses and the total deformation in this model. The material properties are given over here. We have to create a new material whose Poisson's ratio is 1 e raised to 6 psi. Poisson's ratio is 0.35. The force acting on these tabs over here is 5 lbfs. All the model dimensions are given over here and they are into inches. So now let us create this model and solve it. Okay. So we will come to the Ansys Workbench project window, and now I will add one static structural analysis system. I will rename my system. Now the first thing that I need to do over here is I need to create one new material. I will call this as mat2. Okay, and then I will add the Young's modulus, that is 1 e raised to 6 psi, and the Poisson's ratio is 0.35. Okay. After this, we will return to the project and then we will create the geometry. Now in this case, if you notice that the thickness of the geometry is very less, so I can solve this as a 2D problem and a 3D problem both. I will take this as a 3D problem only. Let us go into the design modeler. Once we are into the design modeler, set the unit system as inches because the model is into inches. And now let's start creating the model. So I will take the XY plane and we will enter into sketching. Now look at the dimensions first. The length is 4.8 inches and the width is 5.6. Okay, so 4.8 and 5.6. So I create one rectangle. You give the dimensions. H1 is 4.8, this is 5.6, and then I'm going to add one symmetry constraint so that it is placed symmetrically. Okay, modeling. The thickness, if you see, it is 0.3 inches. So we will extrude this model. The depth is only 0.3 inches, right? So this is the model that we have. Okay. Now what we will do is, we will create a cutout over here. Okay. We will create a cutout. The thickness of the model is 0.05. Okay. So I will come back over here. I'll select this face and go into sketching. Once we come over here, I'm going to draw one rectangle whose dimensions are this is 0.5, H3 is 0.05, and this over here is we've drawn it in the wrong direction. I will just change the sketch. Let me delete this. I have to create the sketch in this direction. Dimensions. This, and one vertical dimension over here. So this is 0.05. V6 is 4.7, and this over here is 0.5. Modeling, extrude. I need to cut the material. Once this is done, I'm going to create a shell, and I will say faces to remove. This is the face, and this is the face, and the thickness should be 0.05. So this is the model that we have to create. I need to make one change over here. This face also has to be removed. So as the faces to remove this, and this. Okay, so this is the model. See it carefully whether you have the same model that we want. Okay, the model is ready. This is the plastic CD case that we wanted. Now after the geometry is ready, we will then enter into the mechanical model. So double click on the mechanical model. Once you come over here, the first thing that we need to do over here is that I need to change my material. Then we will mesh the model. So I'm going to use the default mesh settings for creating the meshing over here. You will observe that we've got 3D tetrahedral meshings over here. You can add one mesh method for this body, and I can try to achieve X dominant meshings, and we'll update this. We can try to achieve X dominant meshing. Now if we click over here, we've got this. We can use the relevance option to make it much more finer. Okay. Once this is done, if you feel that it is not very good quality, you can delete this X dominant option, and we can add the proximity and curvature options. Then we will update it. So now you will see that the mesh will become much more finer because of the advanced size option. It will take some time to generate because of the small element sizes. So you will observe over here that the mesh has become very fine. Okay, so because the meshing has taken a very long time to generate, it will also take a very long time to solve. So instead of using the proximity and curvature option, we will switch it off. We will switch off the proximity and curvature option, and we will use the default mesh settings. Okay, if you want to make it finer, you can use the relevance options. Okay, or else you can give the element size a default element size. I'll say the default element size should be of 0.2 inches or maybe of 0.1 inch. Okay, so this has become slightly finer. Okay, So once the mesh has been done, then we will apply the boundary conditions. So according to the model, we have seen that if you see in this PPT, the boundary conditions are mentioned over here. Okay. Now let us apply the same boundary conditions in the design. I'm going to apply one frictionless support on the basis over here. Now the frictionless support, when you apply a frictionless support on a face, it restricts the normal direction motion. Normal direction means, now the normal direction to this face is actually the z direction. So this face is blocked in the z direction, but the tangential motion, that is the tangential motion in x and in y are available, plus the rotational and tangential direction is available. After that, I'm going to apply forces. The first force I'm going to apply in this face, on this face, and it has the value of 5 lpf. And the direction of the force, I'll use this line over here to apply the force direction. So you can see that the force has been applied. Similarly, I need to apply a similar force, same value, same magnitude, but the direction is different. So it is 5 lbf, but the direction is, swap the direction. And now we will add the results. What results do you want? I want the total deformation and the equivalent stress. Let us solve. So once you solve, you can see the results that we've got. So the stress value that we've got is 21,409 psi, and the total deformation value is 0.1 inch, which is very, very high, right? Now, we need to understand whether the result that we've got, the stress value that we've got, is accurate or not. Okay. So if you remember in the starting chapters, we have spoken about optimum mesh size. How do you decide on the optimum mesh size? Okay. Now, if you want to understand whether the results that we've got is correct or not, what do we do? Okay. We have a stress value. Now we go on refining the mesh. As you refine the mesh, the stress value will increase. But after a certain point, the stress value will almost become constant. It will not increase any further. So from this I can judge whether that this over here is the optimum mesh size. I should not further refine it, because the answer is almost going to be constant. Okay. So what we will do is we will refine the mesh. Now, where exactly should I refine the mesh so that I get accurate answers? To understand that, we will add one more option, which is called as structural error. Now first let us understand what this structural error is. Now structural error is nothing but it is an option by which the user can understand, or they can recognize that region in the design where if the mesh is refined, the solution will become more accurate. Okay. So in this figure you can understand that after the structural error calculation, it has designated, or it has pointed out to that region which, if I refine the mesh in this area, my stress solution will become more accurate. Okay. So now let us do the same thing in our case. Okay. So now if you see that if we refine the mesh in this region, our stress answer will become much more accurate. Okay. Now the refinement that we are talking about, okay, this refinement, you go on in reducing your mesh size to refine. This refinement can be done manually, or you can use an automated procedure in Ansys Workbench, which is called as convergence. Now first let us discuss about convergence. Now, convergence is a tool that is available in Ansys Workbench which controls the accuracy of a solution. Okay, and convergence tool can be added or can be used in static structural analysis, modal analysis, linear buckling analysis, steady state thermal analysis, and magnetostatic analysis. Apart from this, you cannot use convergence in any other analysis system. Okay, and to use the convergence tool, you should enter a value in the allowable change criteria. You should, as a user, you should specify this value. By default, this value is always at 20%. Okay. Now let us understand how this value is used and how the convergence works. Now let us say currently we are using a mesh size of 0.5 inches. Okay, or 0.1 inches. Okay, let us say we have used 0.5 inches. At 0.5 inches, we are getting a stress value of 24,609 psi. Now from here, if I refine my mesh to 0.2 inches, I might get a solution up to 30,000 psi. This is just an example for you to understand. After that, if I further refine, you will get another solution. Okay. Now, the allowable change, suppose if the allowable change that you have given is 10%. Okay, 10%. So, in the first iteration, this is the answer. In the second iteration, this is the answer. So, if the solution, if the result in the first iteration and the second iteration, the difference in both the values is less than 10%, that means your convergence is successful. It is successful and we have got the answer. But if the allowable change, okay, if the solution that we've got is more than the allowable change, that means the difference between the two values is more than 10%, that means your convergence procedure is unsuccessful. Okay. The lesser the value you put over here, the more accurate answers you will get. But it will take more time because it will have to do more number of iterations. Okay. So now let us understand how to perform the same in Ansys Workbench. Okay. What we will do is, let us add one convergence tool. So right click on the option, means you want to do convergence for which option? For the total deformation or for the stress. So I'll select the stress and we will add one convergence tool. In the convergence tool, you need to enter the allowable change. So currently, let us say the allowable change is 20%. I will keep it at the default value, and in solution mode, you have to click the number of iterations you want. The maximum refinement loops is nothing but the iterations. Let us say we go for 2 iterations. Okay, and now we will solve. So now what the software is going to do, it will, in the first iteration, it will refine the meshing to first level, and then again it will calculate the answers. If the answer, the difference between the two solutions is lesser than 20%, it will stop, otherwise it will continue. Again it will go for the second iteration, and then again it will refine the mesh and record the answers again. So now we have to see whether the convergence procedure is successful or not. Okay, so now we see a red colored exclamation mark over here. That means the convergence process is not successful. Let us click on convergence and let us look at the graph. So the first, where we started, we had 5,731 elements and the answer that we recorded was 21,409 psi. After which, in the first iteration, the number of elements were increased to 7,845 elements and the answer increased to almost 30,000 psi, which recorded a percentage change of 33%. So the difference between the two is a 33% change. Later on, if you see, the answer has again increased and the percentage change is 30%. Now if you see, the answer is not becoming stable. Okay. The reason for this in our case is, stress singularity. We are not getting a stable answer because of stress singularity. Now let us understand what is stress singularity. Now stress singularity can be major concerns in the results because of stress singularity your answers will change or they will distort considerably. Okay, and these stress singularities can be a major reason why we don't get the convergent solutions. Okay, stress singularity can happen because of many reasons. Now let us understand what these reasons are. Stress singularity can occur when you are applying constraints on points, small edges or faces with sharp corners. Okay, now look at this example over here. We have a force which is acting at this point over here. Okay, now the stress formula is force upon area. So the value of the force upon the area on which it is acting. So when you apply a force on a single point or on a sharp corner, the area is almost zero. So if I divide something by zero, the stress becomes infinite. Okay, so this is again a reason of stress singularity. Whenever you apply forces on small edges, on small areas or on points, there can be a situation of stress singularity. Okay, so you should avoid such cases. The second reason can be whenever there are sharp corners in your design. Okay, in those sharp corners your stress concentration is very high. Now what happens is whenever you go for convergence, whenever you go for refinement of meshing, these stress values will go on increasing, and what happens is in those sharp corners cracks start developing. Now these cracks will only go on increasing and the stress value will never reduce. So what we should do is we should never have sharp corners wherever the boundary conditions are acting or wherever stresses are more. You should always try to add fillets in those regions. Now according to our situation, the stress is very high in this region, right? So what we can do is we can add a fillet over here so that the cause of stress singularity is eliminated and we get correct answers. So what for this I will again go back to my geometry and we will add a fillet over there. So we will come to the fixed radius option. I'll select this edge and I will select this edge. Use your control key to select both the edges and then enter the value of the fillet. Okay, if you want to reduce the fillet, I can change the value. I'll say it has to be a 0.1 radius. Now that you have entered the fillet, we will again come back to the mechanical model. Let the model get updated. Now once the model has updated, we will have to redo the meshing. So update the meshing once again. See the number of elements. Okay, and now we will perform the convergence check again. Okay, for time being you can delete the convergence. Record the stress value first. What is the first stress value that we get? You will see that the stress value is somewhere around 34,000. Initially we were getting 21,000. So now you are getting much accurate results in the first attempt itself. After that, you can see the area of structural error. So if I refine the mesh over here, you will get much more accurate results. Now we will add the convergence tool again. The allowable change is still 20%. Refinement I want 2 refinements, and now we will solve again. So previously, because it was a sharp corner, we did not get any convergence solution. Now we will see if because of adding of the fillet, will we get better solutions or not. So in the first iteration itself, if we get the allowable change is lesser than 20%, we will get an answer over there. Otherwise, it will proceed to the next iteration. Okay, now can you see that there is a green colored tick mark that appears in front of the convergence tool? That means we have got a solution. Now look at the graph changing. It has almost become stable. Okay, now can you see in the after the first iteration the allowable change was 23%. Okay, but in the second iteration the elements were increased from 8,398 to 16,323, and the answer that we got is almost stable. Okay, and we've got the best possible answer for the solution, that is it is 43,005 units, 5 psi, 43,005. That is the answer that we got. So from this example you have understood few more concepts in static structural. That is, we understood what is the structural error. After that, we understood what is the meaning of convergence and how we can use convergence. And after that, we have also understood what is stress singularity. Okay, so this is a very good example from which we have understood 3 more concepts and also how to perform the analysis. Okay.